Fillers in construction adhesives and adhesive joints. Construction adhesives are widely used in the building industry to improve the strength, durability, and integrity of structural assemblies. These adhesives serve several functions, including reinforcing concrete and metal structures, bonding composite materials to existing structural elements, and joining dissimilar materials such as ceramics, polymers, metals, and fiber-reinforced composites. In such applications, the mechanical performance of the adhesive, particularly its tensile, compressive, and shear properties, is critical for ensuring structural reliability. A common application of construction adhesives involves post-installed anchoring systems. In this method, steel reinforcement bars are inserted into drilled holes within hardened concrete and secured using adhesives. The adhesive fills the gap between the steel bar and the surrounding concrete, forming a strong bond after curing. Epoxy adhesives are frequently used for this purpose because they exhibit strong adhesion to both concrete and steel while remaining relatively economical. However, neat epoxy systems often have limited mechanical strength and shear resistance, which necessitates the incorporation of fillers to enhance their performance. Epoxy adhesives are also widely used in structural strengthening applications, such as bonding carbon fiber reinforced polymer (CFRP) composites to steel or concrete structures. These composite reinforcements are commonly used to improve the load-bearing capacity and durability of infrastructure components. Adhesives are also essential in architectural glazing systems, including overhead glazing, safety glass installations, and walkable glass structures. In these applications, adhesives enable point-fixed glazing, allowing glass panels to be securely bonded to supporting structures. The addition of fillers to construction adhesives serves several important purposes. Fillers can reduce formulation costs, increase stiffness and rigidity, minimize shrinkage during curing, and expand the temperature range over which the adhesive can operate. Common fillers used in construction adhesives include silica, alumina, carbon black, graphene, carbon nanotubes, talc, lime, nanoclays, and metal particles. The effectiveness of these fillers depends strongly on parameters such as particle size, morphology, surface chemistry, and dispersion within the polymer matrix. These factors influence the resulting adhesive properties, including bond strength, fracture toughness, and durability. Adhesive bonding is increasingly regarded as a viable alternative to traditional structural joining methods such as mechanical fastening, welding, and soldering. Compared with these techniques, adhesive joints offer several advantages, including the ability to join dissimilar materials, reduced structural weight, simplified design, and improved resistance to fatigue, corrosion, and environmental degradation. Adhesive bonding also distributes stress more evenly across the joint, minimizing localized stress concentrations. Certain composite materials, particularly carbon fiber, epoxy, CFE, composites, are difficult to join using mechanical methods. Adhesive bonding therefore provides a more effective method for connecting such materials to metals or other composites. Fillers are also used in specialized adhesive systems such as photoactivated adhesive work holding, PAAW. In these systems, UV-curable adhesives filled with materials such as glass fibers or glass spheres are used to temporarily hold workpieces during machining operations. These fillers, which may range from micro to nanoscale dimensions, reduce volumetric shrinkage during curing. Other inorganic fillers, such as silica and alumina, are also commonly used in adhesive joints because of their high mechanical strength and thermal stability. Inorganic fillers in construction adhesives. Silica, silicon oxide, is one of the most widely used fillers in epoxy adhesives. It can be incorporated into adhesive formulations in the form of microparticles or nanoparticles. Silica-filled epoxy adhesives are commonly used in anchoring systems where the adhesive fills the gap between steel reinforcement bars and concrete before curing. Microsilica-filled adhesives are also used in structural bonded joints. The silica particles may be of a single size, for example 25 micrometers or 50 micrometers, or may consist of hybrid mixtures of particles with different sizes. Incorporation of silica fillers generally increases the flexural modulus and tensile modulus of the adhesive, although flexural and tensile strengths may slightly decrease because the rigid filler particles can introduce stress concentration points. Smaller silica particles possess larger surface areas, which enhances interfacial interactions between the filler and the epoxy matrix. As a result, properties such as compressive modulus, compressive strength, and pull-out strength improve. Hybrid fillers containing particles of multiple sizes can further enhance mechanical performance, leading to improvements in tensile and flexural properties. Silica nanoparticles are also used in lap shear joints involving stainless steel substrates. To prevent particle agglomeration and improve compatibility with the polymer matrix, the nanoparticle surfaces are often modified using coupling agents such as silanes. The addition of silica nanoparticles improves the tensile strength of adhesive joints. However, high filler loadings, around 40 weight%, significantly increase adhesive viscosity, reducing wettability of the steel surface and potentially lowering bonding efficiency. Surface hydroxyl groups on silica nanoparticles can absorb water molecules during hygrothermal exposure. These absorbed water molecules can form hydrogen-bonded bridges between epoxy chains, thereby increasing the storage modulus of the adhesive joint. Consequently, silica fillers may provide beneficial effects even under humid conditions. However, combining silica nanoparticles with microsilica in adhesive formulations may reduce mechanical properties such as compressive, tensile, and flexural strength. This occurs because excessive hydroxyl groups on the particle surfaces can reduce compatibility with the epoxy matrix. Surface modification through silanization can improve filler matrix interactions and restore adhesive performance. Alumina, aluminium oxide, nanoparticles are commonly used to enhance the performance of structural adhesives. In metal-to-metal bonding applications, such as aluminium-to-aluminium lap joints, the incorporation of alumina nanoparticles improves peel strength and overall bond strength. The shear strain behavior of the adhesive depends strongly on filler concentration. As alumina loading increases from 0 to approximately 0.5 weight%, the maximum shear strain increases. However, when filler content increases further to the range of 0.5 to 1.5 weight%, shear strain decreases due to reduced polymer mobility and particle agglomeration. The elastic modulus of the adhesive increases with filler addition up to approximately 1.5 weight%, after which a slight reduction occurs. This reduction is attributed to poor dispersion of nanoparticles or increased stiffness that limits stress redistribution. The morphology of alumina nanoparticles also affects adhesive performance. Both nanoroids and nanospheres have been used as fillers in epoxy adhesives for aluminium alloy lap joints. Shear strength increases significantly when alumina nanoparticles are added. For example, neat epoxy adhesives typically show shear strength of approximately 4.39 megapascals, whereas adhesives filled with 1 weight% alumina nanoroids can reach 6.83 megapascals. Adhesives containing 1.5 weight% alumina nanospheres exhibit shear strengths around 6.68 megapascals. These improvements result from efficient stress transfer between the nanoparticles and the polymer matrix. Limestone. Mineral fillers play an important role in tile adhesives used for bonding ceramic tiles to concrete substrates. Carbonate-based fillers derived from limestone or marble and silica-based fillers derived from quartz sand are commonly used. In epoxy adhesives, increasing limestone filler content from 2.5 weight% to 10 weight% decreases the bulk density from approximately 1,440 kg per cubic meter to 1,370 kg per cubic meter. The presence of limestone filler does not significantly affect the water retention capacity of the adhesive. Initial adhesive strength and strength after thermal aging increase with limestone addition. However, adhesive strength after prolonged water immersion decreases, particularly when fine limestone particles are used. In addition, higher limestone content can increase the slip of ceramic tiles on concrete substrates and reduce the flexural strength of the adhesive. Iron powder. Metal powders are sometimes incorporated as fillers in epoxy adhesives used for aluminium bonding. Iron powder with approximately 80% iron content and particle sizes ranging from 100 to 200 micrometers has been used to reinforce adhesive joints. Iron particles improve the resistance of adhesive joints to crack propagation. At low filler volume fractions, failure occurs primarily through cohesive fracture within the adhesive layer, whereas at higher filler concentrations the failure mode shifts to adhesive fracture at the interface. Maximum peel and shear strengths are observed at approximately 30 volume% iron filler, where peel strength reaches 2.48 megapascals and shear strength reaches 9.38 megapascals. When filler loading increases to 60 volume%, both strengths decrease dramatically, with peel strength falling to 0.43 megapascals and shear strength to 0.23 megapascals. In general, shear strength of the joint remains significantly higher than peel strength. Despite the presence of metallic filler particles, iron-filled epoxy adhesives typically do not exhibit substantial electrical conductivity. Titanium dioxide. Titanium dioxide, titanium 4 oxide, nanoparticles are used as fillers in epoxy adhesives for copper-to-copper lap joints. Adhesives containing about 10% weight titanium 4 oxide show improved wettability on chemically treated copper surfaces compared with neat epoxy. Titanium 4 oxide nanoparticles increase the toughness of adhesive joints but also increase adhesive viscosity, resulting in thicker bond lines. Lap shear strength increases as titanium 4 oxide concentration increases up to about 10% weight, but decreases when filler loading reaches 15% weight. The initial improvement is attributed to increased resistance to cohesive fracture, while the decrease at higher loadings results from reduced interparticle spacing and stress concentration. Titanium 4 oxide nanoparticles can also reinforce two-component acrylic structural adhesives used for bonding steel and glass, epoxy composite beams. At approximately 3% weight filler loading, shear strength and tensile strength increase by 47% and 59%, respectively. Higher filler concentrations lead to nanoparticle agglomeration and pore dispersion due to increased viscosity, resulting in reduced mechanical performance. Zirconium oxide. Zirconium oxide, nanoparticles are used as fillers in epoxy adhesives for bonding aluminium sheet structures. Increasing filler content raises both adhesive viscosity and bond line thickness. Adhesive joint strength increases as zirconium oxide concentration rises from 10% weight to 15% weight, primarily because the nanoparticles enhance fracture resistance. However, further increases to 20% weight reduce joint strength due to particle aggregation and increased stress concentration within the adhesive layer. Carbon-based fillers. Carbon nanotubes. Multi-walled carbon nanotubes, MWCNTs, are highly effective reinforcing fillers for epoxy adhesives used to bond CFRP composites to steel structures. These adhesives are commonly used in double strap joints and single lap joints. Uniform dispersion of nanotubes within the epoxy matrix significantly increases the tensile strength and Young's modulus of the adhesive. Although the stiffness of nanotube-filled adhesive joints is similar to that of unfilled systems, the bond strength increases because nanotubes enhance load transfer across the adhesive layer. Adhesives containing MWCNTs also reduce the effective bond length required for structural joints and allow CFRP laminates to sustain higher ultimate axial strain, improving structural performance. Graphene nanoplatelets. Graphene nanoplatelets, GNPs, are another promising reinforcement material for epoxy-based construction adhesives. These nanofillers possess a large specific surface area, extremely high Young's modulus, and high tensile strength, making them excellent reinforcement agents. The addition of graphene nanoplatelets improves several mechanical properties of adhesives, including shear strength, shear modulus, fracture toughness, and strain at failure. As graphene content increases, the adhesive nanocomposite exhibits enhanced load transfer capability between the filler and polymer matrix. Consequently, graphene-reinforced epoxy adhesives show significantly improved mechanical performance compared with conventional construction adhesives. Conclusion: fillers play a critical role in improving the performance, durability, and functionality of construction adhesives and adhesive joints. While polymeric adhesives such as epoxy and acrylic systems provide strong bonding between structural materials, their mechanical limitations, particularly in terms of stiffness, strength, shrinkage, and thermal resistance, often necessitate the incorporation of reinforcing fillers. By carefully selecting and incorporating fillers, it is possible to tailor the physical, mechanical, and thermal properties of adhesives to meet the demanding requirements of construction applications. Inorganic fillers such as silica, alumina, titanium dioxide, zirconium oxide, limestone, and metallic powders significantly influence the structural performance of adhesive systems. These fillers generally enhance properties such as elastic modulus, compressive strength, fracture resistance, and bond strength when used in optimal concentrations. However, excessive filler loading can increase viscosity, promote particle agglomeration, and reduce wettability, which may negatively affect bonding performance. Therefore, parameters such as particle size, morphology, surface chemistry, and dispersion within the polymer matrix must be carefully controlled. Carbon-based nanofillers, including carbon nanotubes and graphene nanoplatelets, represent an important advancement in adhesive technology. Due to their exceptional mechanical strength, high surface area, and excellent load transfer capability, these nanomaterials can significantly enhance tensile strength, shear properties, and fracture toughness of adhesive joints even at relatively low filler concentrations. Their incorporation into epoxy adhesives has shown considerable promise for strengthening structural joints involving fiber-reinforced composites and metallic substrates. Overall, the incorporation of fillers transforms conventional adhesives into high-performance composite materials suitable for demanding structural applications in construction and infrastructure. Continued research on filler surface modification, dispersion techniques, and hybrid filler systems is expected to further improve the mechanical performance, durability, and multifunctionality of adhesive joints used in modern construction technologies.